Welcome back. This week, we're going to talk about correlational research. Our roadmap today includes 3 parts. First, we're going to have the major portion of today's lecture on correlations, which are the most basic form of correlational research. We're then going to segue into regressions, which help to build upon correlations, moving from just understanding the relationship between variables to predicting one variable from the other. And then finally, we're going to end on multivariate analyses, which are when you take more than 2 variables and see how they're related to each other. So let's start by describing what we mean by correlational research. And that is when we measure relationships between 2 or more variables that are within the same group of people. So the same individuals are scoring on one variable and the other, and how are those 2 scores related to each other? These variables are measured, but they are not manipulated. We are not affecting them. We are just seeing the relationship between those 2 variables. And because we are not manipulating anything, it means we can't determine that causation. Now, if we are doing multiple variables, then we're going to be doing a multivariate analysis. But most of the time, we're just sticking with 2 variables, doing what's called a bivariate correlation. Or at least, I should say, most of the time in this course, we're going to be focusing on that. In fact, you know, for your project, some of you have chosen to do 2 continuous variables to see how they're related to each other. That again is a bivariate correlation. This is when you're finding the statistical relationship between exactly 2 variables, and it is usually the most appropriate when both measures are continuous, just like your project. You're trying to find if the changes in one variable, your variable x, are systematically related to the changes in the other variable. And what do I mean by changes? I mean increase or decrease. So as your x variable increases, is there a systematic response from the y variable? Does it also increase, or does it decrease, or does nothing happen? And vice versa, if you have some change in y, either increasing or decreasing, is there a systematic response from x, or a systematic relationship with x? As an example, we might be running a study that's trying to find whether weight varies by age. The question here is, as age increases, is there a systematic increase or decrease in weight? Do we see some change that we can identify a significant relationship between our variable x of age and our variable y of weight? When we are running correlations, we are going to represent those relationships in 2 ways, or describe those relationships in 2 methods. The first is through scatter plots, which we've seen before. These are the graphic representations of how the variables are related to each other. We saw this when we were describing negative, positive, and zero effects, the quick correlation intro when talking about reliability. So we had the example of auto mileage and auto value. As the mileage increases, the value decreases. We had the auto quality and auto body color where they were not related to each other. And then the number of accidents versus the insurance cost, that as accidents increases, so does insurance cost. So we can represent it with this visual graphic representation. But we can't do a representation for everything, or we might not have space to put a graphic everywhere. So we also want to come up with a coefficient, which is our statistic. And this tells us about the strength of those relationships. So you have here an example. It goes from -1 to 1. And we can see where some of the strong, weak, and negative, positive are on this relationship. Now, I want to be clear with correlational research that they are both merely descriptive, these scatter plots and coefficients. No causation is ever inferred when we are talking about correlation. You heard it before. I'm going to say it once now. I'm going to say it again. Correlation does not imply causation. There, I got it out of the way. I said the thing. All right, but we're going to talk about what that means a little bit more. So let's start with discussing scatter plot. Again, you've seen scatter plots before when we were talking about reliability. We're just going to go into it again to make sure everybody's clear on what their purpose is. So anytime you're doing a correlation between 2 variables, again, that each person has a value on both of those variables, you want to plot it on a scatter plot. For example, we might use age and how long people have been smoking. And what we're going to do is take this graph, and we have an x and a y axis, and on each of those x and y axes, we're going to put the scores for one of the variables. And the way we are plotting each individual is where does their score kind of match up. So you have one participant who at age 20 also had been smoking for 60 months. You then have an age 50 who had been smoking for 240 months and an age 32 who had been smoking for 300 months. And you are going to put all of those individual people onto the scatter plot. And in case you were wondering why it's called a scatter plot, it's because you are plotting a bunch of scattered dots, right? There is no specific line here. There's just a scattering of these plotted points that are marking each person's score. And this is done for every person who is in your sample. Obviously, we can't do it for the whole population. We are just doing it for the people we collected the data, and it'll be inferential. And once you have drawn that scatter plot, you can then overall eyeball that pattern, see if you see any trends, see if there's any outliers, which are data that don't look like they fit the general pattern. You're just going to look at it and see, do you see any kind of messaging? For instance, here I have a bunch of different scatter plots, and you can see how some of them are more spread out, some are more clustered, and some are very clustered along a line. And depending on how spread out or clustered these data points on the scatter plot are, is going to determine how significant and how strong of a correlation you find. Now, typically, when we are representing our correlations, we're going to use a correlation coefficient. And this coefficient just simulates the degree of covariation. We've seen that word covariation. It's how do two things co-vary? Do they vary at the same time? And co is always together. This again requires scores on both variables for each participant. If a participant is missing a score on either of the variables, they are not calculated into your correlation coefficient. They are just skipped. You pretend like they are not in the sample at all. And the correlation coefficient that you're going to see most often is the Pearson correlation. This is represented by a lowercase r. This is the most commonly used, and it ranges from -1 to 1 on a scale where 0 means there's absolutely no relationship, and then the further the score is, that r score is from 0, the stronger you consider the correlation. Here at the bottom of the screen, we have that represented visually. You can see it ranges from -1 to 1, and the 0 right in the center is that no relationship. And this helps to illustrate both the magnitude and the direction. Now, I've already kind of described magnitude when I talked about the strength. The strength is how far away from that 0 it is. With the further away, closer to -1 or 1, means you have a stronger relationship. Whereas if it's closer to 0, it is a weak relationship. In fact, exactly 0 means there's absolutely no relationship in any way, shape, or form between two variables. Whereas a +1 or a -1 signifies that these variables could not be more related, that a change on one variable will always be associated with a similar kind of change on the other variable. But what kind of change are we describing there? Well, that's the direction of the relationship. A positive relationship, so moving from 0 to +1, that signifies that as one changes, the other variable changes in the same way. So maybe both variables are increasing together, they are varying by increasing together, or they are both decreasing at the same time. As one lowers, the other lowers. A negative relationship implies that they have opposite responses. As scores on one variable increase, then the other score is going to decrease, and vice versa, that as one variable decreases, the other increases. So what we're trying to find is how much do they change or not change together. That -1, negative, a perfect, strongest negative relationship you could have, means that every time a score on one variable increases, that means you know that the score on the other is going to decrease. Right? Whereas positive can increase and increase together, or decrease and decrease together. So here's another representation of how all of those correlation coefficients fall along the spectrum from -1 to 1. I want to kind of push here, if I haven't said it already, that a -1 and a +1 are these perfect relationships between variables, and they just don't exist in the real world. There's always going to be some amount of error. Maybe it's systematic, maybe it is response error, maybe it is measurement error, but you will not get a perfect correlation. In fact, if you do get a perfect correlation, you probably did something wrong in your math. Instead, we have this spectrum ranging, and we signify the strength and the weakness of the relationship between these variables based on the number that we're going to generate, that r. So you'll see stuff like the negative 0.77. That is a strong relationship in the negative direction because it is close to 1. In fact, anything that's around a 0.7 or 0.8 is kind of our cutoff. And then if you get any lower, so negative 0.8, negative 0.9, negative 1, those are all going to be strong. Whereas on the other side, we have our strong numbers are the positive 0.96. The 0.54 we might call about a medium there. It's not quite into the strong or a moderate relationship. But once we get down closer to 0, so around a negative 0.23 or a 0.08, then we're starting to say, look, this effect, this correlation is so weak. Now, nothing I've talked about so far has anything to do with significance, which is a term we're going to talk about later. Instead, we are only talking about the magnitude and the direction. Here are those clustered analyses again, the scatter plots, and you can see how the ones that are very unclustered, the ones that are spread out, scattered all over the place, there's not very a clear message about the relationship between them. Those are going to be those weak relationships around an R of 0, or even an R of -3 there on the second one, where you see there might eyeball a little bit of a negative slope, a negative downward trend of that relationship, but it's not a strong story there. The moderate ones of the 0.7 or the 0.5 or the negative 0.7, you can see in the scatter plot that there is much clearer of a message, but there's still a lot of error. Not everything fits together or perfectly relates to each other. Whereas with the high positivity, when you have extreme clusters where that last example is almost a straight line down, there you're going to have a correlation that is very close to 1 or -1. There, that 0.9 or even the -0.99, which is ridiculous and almost never happens in the real world. Okay, so you see how the spread and the clustering has a correlation with how strong the relationship is, how strong the correlation is. Well, let's get some practice with how this might look if we were actually doing a study. So here we're trying to look at the relationship between weight and height. And we have collected a sample of participants. Here we have 8 participants who have all given us both their weight and their height. And we want to know, are they related in some way? So first, we're going to do that scatter plot. It's important to note here that every subject has both a score on weight and height, so we can include every subject in our correlation analysis. So we go to our scatter plot and we take each point of data and we put it on with weight along the x-axis and height along the y-axis. X is always the horizontal and y is always the vertical axis. So here we have Mary with about a 110 and a weight of 62. Then we have Andrea, we're going to put in John, there's Terrell, and then we're going to put the other 4 people in there as well. So we have all 8 data points. And you would first look at this and try to eyeball what kind of relationship you're seeing. I'll give you a second. Okay, so think about it. What is the strength and the direction that you're seeing here? Now, the direction might be the easier part. Here we're having about a linear positive relationship. So it is going up. As people's weight increases, we're also seeing that their response to the height is increasing. And as people respond that they have lower weight, we also see a lower height. So there seems to be a positive relationship between these. And when there is a line that we can draw between them, between the items, it doesn't necessarily pass perfectly through all of them, but when we can kind of represent a hypothetical line, it is called a linear relationship, because linear. And we see that it is upward, the increasing, so we have a positive relationship represented here. Another way to visualize this Pearson coefficient for yourself is to go into your actual data and sort it based on your x variable. For us, that's weight. So here we have descending order Terrell at the top with 193 and Mary at the bottom with 110. And then just like a scatter plot, we can eyeball what does the change in height look like. So we see that Terrell, who is the heaviest of our subjects, also had the tallest height. and Mary had the shortest height, and that the people in between seem to be in general decreasing in their height as they decrease in their weight. Now, it's not necessarily perfect decreasing. It doesn't decrease in the same steps, but it is still kind of in the same direction. And in fact, if we were then to go on the next step and try to find the coefficient, we would see that the R value, that Pearson coefficient here, is a positive 0.925. This is very strong because it is close to that 1.0. In fact, anything over a 0.8 is usually understood as very strong. It's also positive because it's in the plus side, and as one is increasing, the other is also increasing. Or you could frame it the other way, that as one decreases, the other also decreases. You can switch and swap these when you're doing a correlation because the order doesn't matter and the direction doesn't necessarily matter as long as you're keeping in mind what the relationship is. So once you've described a Pearson coefficient based on its magnitude and its direction, what do we do next with interpreting it? And this is going to go back to the idea of effect sizes. These are an indicator of the relationship between two variables. How much do they covary? And as I've described already, the Pearson R is exactly that, describing the relationship between two variables. And in fact, a Pearson R is a measure of effect size. And a stronger Pearson coefficient is the same thing as a stronger effect. And in a scatter plot, you can see this by how tight the data is to the line. The more spread there is, the more kind of all over that scatter plot, away from the line of best fit that you are drawing through the data, the more close it is to that line, the stronger the effect, whereas the more spread it is, the weaker the effect. In fact, as you spread out the data a lot, it'll start to turn into a zero correlation because there's no clear line that can be drawn. So just as we saw in the earlier images, if it is almost an immediate line, you can see exactly how the dots follow on a trend. That is going to be an extremely high effect. But why do we care about these effect sizes? The main reason is because large effect sizes can lead to more accurate predictions. Now, this is the first time I've really used the word predict. So far, I've tried very carefully to use the related to each other. But if some two variables are extremely related to each other, that as one increases, the other pretty always is increasing also, this allows us to then get a piece of information about an individual, one piece of information, and guess about how they're going to be doing on the other. This is that prediction. And this is the basis of regressions, which we're going to talk about a little bit later in this video. Now, I want to say that the accuracy is very important, and you will also notice that there's something related between accuracy and reliability, which we talked about before, and we were using correlations to describe reliability and accuracy. So you're going to see that a lot. But I also want to talk about importance. So some people believe that a large effect size equals a more important effect. That if there is a strong relation between two variables, then it's showing they really matter with each other, that one is maybe having an influence on the other, or they are both systematically changing for some important reason that helps us to understand the world. And this is sometimes true. And a lot of times it's great research and it's really easy to look at the link between two variables and say, wow, that's great. But it's not always true that a large effect size is important, or I should say some important effects are actually really small. For instance, there's a number of studies about the use of aspirin as heart medication. And when the original studies were coming out to find out whether aspirins help to defend against heart attack, they actually had a really low effect size. It was a very small effect size. That people who took aspirin weren't necessarily having an incredible response to it that was decreasing heart. And that's largely because there are so many other factors that play into heart illness. But the aspirin was more effective than anything else. Any other behavior had almost no effect size, but aspirin did, albeit a small effect size. But that small effect size, still when you look at it on the scale of the millions of people every year who are taking aspirin or potentially suffering from heart illnesses, well then that starts to matter, right? Because as you're increasing the number of people who are using it and the frequency that they're using it, that effect size gets to compound. And so the importance of it is not necessarily linked to the size of it. Aspirin, still important, even though small effect. Now, once we understand the interpretation of an effect, we then might want to compare effects to each other. And so we ask ourselves, is an effect size or a Pearson coefficient of 0.8 twice as large as a 0.4? And the answer to this is no. The Pearson R is not a ratio scale. If you'll remember back to the nominal, ordinal, interval, and ratio scale implies that there can be some kind of math about it, that there's a meaningful zero that means no relationship. But R happens not to be on that scale. You cannot compare them with twice as or half or any kind of math between them. Instead, we have to create a coefficient of determination to do that so that we can compare effect sizes. So a coefficient of determination is telling us specifically about the amount of variation in one variable that can be explained by the other variable. So the key here is that in R, a Pearson R is telling you what is the relationship between each other, and as one varies, how does the other vary? But the coefficient of determination tells you the degree to which one is explaining the variation in the other. And the way you get this is pretty easy. You simply square your Pearson R. So in an example, we might have an R of 0.4. So we square that 0.4 to get a 0.16. And then if we're looking at the percent of variation, we could just multiply by 100. And we could find that 16% of the variable x or the variable y is explained by the variable x. And this is also an effect size. They're both effect sizes. They're just telling you a little bit different information. One effect size, that Pearson R, you can't compare to each other, but the R squared is an effect size that you can't. Again, this is the proportion of total variance that is systematically explained by your x variable. The amount of uniqueness in the y variable that is explained by the x variable. So x may be affected, the y variable, your outcome variable, may be affected by many possible factors, but we are solely interested in the contribution of x. That being said, there's still 84% of the variation in our y variable that might be explained by something else. And that's maybe of interest for later. So as a quick review, we have talked so far about how to visualize a correlational data. We've talked about the Pearson R that represent it statistically, that relationship represented by a number. We've talked about the coefficient of determination, which is one way of interpreting the effect size and comparing effect sizes beyond just the direction and strength of the Pearson R. But we haven't yet talked about the term significance. That's that even after you found a relationship between two variables, does that relationship truly exist in the real world? Is whatever you found in your study representative of the population? And this is associated with a p-value. A p-value is how likely there is in fact the correlation you got from your study in the population, and how likely is it different from zero, that is, no relationship. Again, if you did a study, how likely does that finding exist in the population? So another way of saying this is, if you found a relationship in your sample, how likely is that due to chance, or is it actually true outside of your study? The rule of thumb is that if the probability is less than 5%, that the sample correlation that you found in your study is due to chance, so less than 5% chance that it's just random relationship between two variables, then the results are considered statistically significant and reflect what should exist in the larger population. And all of this is inferential. We are using a small subset sample, and hopefully one that is representative of the population, but there's always going to be some amount of chance and error. We're just trying to figure out how much chance and error is there. So if it's a small amount of chance and error, then we're going to feel pretty good about our finding. And that's when we can actually report that significant. I've told you that if the p-value is less than or is more than 0.05, so if it is non-significant, then even if there is a relationship between the two variables, even if you do get a Pearson R that's positive or negative, you treat it as though there is no relationship. You talk about it as though the relationship doesn't exist, because any relationship you did find in your study can be interpreted as chance. Simply that. It just happened that in your sample there was a relationship, but it's not really real in the population. So I want to make sure it's clear to you that you can't report something as significant or as a relationship unless it is significant, p is less than 0.05. Now these p-values are often influenced by two things: the effect size, which is the magnitude, the bigger effect equals a smaller p-value, as well as the sample size, so how many participants you have. The more participants you have, the more likely you are to get a smaller p-value. And you will see this if you do a difference between running a 100-person study versus a 10,000-person study, where suddenly all of the p-values, even for very small effects, begin to be very small, like a 0.001. So both of these, because they are related to p-values, if you can influence one, you can increase the likelihood of your finding a p-value. Now, it's pretty hard to influence the effect size of your variables and the relationship between them. You don't really have much power over whether height and weight are correlated in the real world, but you do have power over sample size. So if you think that you're going to run a study where there's going to be a small effect, but you do in fact want to find it to be significant, well, then you have to increase your sample size. And this is what we talked about last week with the idea of power. Remember that power is the effect size times the sample size. Well, that power has a direct link to the p-value, or the likelihood of you finding significance. See, it's all related. Of course, just because you get a significant correlation or a strong correlation or a good effect size that's great for you doesn't mean you can fully interpret it as a perfect relationship. And we're going to talk about some of those issues with interpreting correlations. The first is the idea of outliers, which I mentioned briefly. When you are visualizing your data, you want to be looking for these extreme scores that might raise questions about whether that individual or that set of scores actually belongs in the data set. Is there something special going on with some participant in how they responded? This can be for a number of reasons. Maybe it's because the participant wasn't paying attention, or the participant was outside the bounds, or mislabeled something, or maybe they are in fact some kind of special case that breaks the normal trend. And you're looking for two types of outliers. Now, here's a relationship. You're looking for two types of outliers. The first is an offline outlier, where you're seeing something that falls outside the pattern of data. So I have that offline down at the bottom there. This is a relationship between GPA and self-esteem scores, where it looks like there's generally a trend that as GPA increases, participants' idea of themselves and their self-esteem seems to also increase. And then we see that offline, where suddenly there is someone with a very low GPA, but who has a moderately high self-esteem. It pulls away from that line. And what these data that pull away from the line do is they cause more of that spread we talked about earlier. It is less close to that line. And so what it does is it dampens the strength of the correlation. It reduces the effect size. The other way you could do it, though, is with an online outlier, where it falls on the same pattern of data, but it is way far out there, that you have really high self-esteem and a really high GPA. It's beyond it. And what this actually does is it inflates the strength of the correlation. It makes the effect size and the correlation look more significant and more effective than it actually is, because that participant might be answering wrong, but the calculation is going to pick up that outlier, and it's going to factor it in and say, I need to draw a point, I need to draw a line that goes through all my data and this online outlier, and that is going to affect that relationship. So anytime you're running a correlation, if you're seeing a really high correlation, you want to go in and look for an online, something that surprises you with how high of an effect size. You want to look for that online. But if you're seeing something that surprises you as it's kind of a weaker correlation than you expected, go look for those offline outliers. See if there's anybody who kind of looks like something's going on in their data that they're not kind of matching the general trend. Another issue you need to keep in mind when interpreting correlations is the restriction of range. This is when you're doing a study covering an entire variable in theory, but only part of that variable is represented in your sample. Only scores from maybe the top half or bottom half of your scale of the possible scores on a variable are represented. And what this does is artificially reduce the strength of a correlation. So for example, I have again these scores for GPA and self-esteem scores. It looks like it's generally a positive trend that higher GPA is correlated with higher self-esteem. But let's say on self-esteem, we are only surveying sadder, lower self-esteem individuals. So we are not getting the full scale of self-esteem. So we block it off here. So we're only getting those 1 to 2 self-esteem scores. Well, here suddenly, if we're only looking at that data, that's a lot less clear of a message. The linear trajectory between those data doesn't really exist anymore. You have kind of what looks like an outlier there at the top. It's just kind of noisy. But we could do the same thing on the other end. What if we only take the really happy kids? And here we're seeing exactly the same. I should say happy, the high self-esteem individuals. Here we're seeing the same thing of a lot of spread there. That linear relationship isn't clear, when if we had taken the full representation of self-esteem scores, we would have gotten, in fact, the linear relationship there. So this can be misleading if you are restricting your range. Another time you might see issues with the restriction of range is when your data doesn't quite fit a linear representation. So I've used the word linear to describe a line that you can draw through the data, a very clear line, whether it's a flat line or a positive or a negative. But sometimes there might not be a straight line that represents your data. Maybe the relationship is more of a curved line, that curve, a linear. In which case it might be that as things are positive at one end, they're negative at a different end. Maybe it's represented by a U-curve like we see here. So here we see that there is initially a positive relationship between GPA and self-esteem, but it kind of balances out and then even converts into a negative relationship. And so here, if we were to draw a correlation between all of the data, how do we fit that line? Well, we probably just have to draw a pretty straight line through the data, which would be a weak correlation. The straight line wouldn't work, but we might be able to do a curved line, a U-shaped, and there's ways to do that. There's different mathematics that are different from our Pearson correlation. So if you get a Pearson correlation that is flat, you should still always be, or that's zero, it's still always a good idea to have those scatter plots that you look at to say, why is my relationship flat? Or maybe there's something else going on. That's why at the beginning of these slides and this video, I recommended looking at your data, not just the Pearson coefficient, the statistics side of it, but also that graphical representation through the scatter plot. Now, I mentioned at the beginning of this slide that this can be an issue for your restriction of range, because what if you were only collecting people with certain self-esteem scores? For instance, I only collect individuals who have high self-esteem. Well, here, if I was doing this study with only the high self-esteem individuals, my report would be that there is a negative relationship between GPA and self-esteem scores. But that's not necessarily true. Or maybe I did the other side, where I said the GPA and self-esteem are positively related because I'm only collecting low self-esteem individuals. Or maybe even I'm just collecting people who are in the middle of the self-esteem spectrum, in which case I don't really see a strong relationship at all. It's kind of a weak flat line, lots of noise in this relationship. None of the three of these are really the relationship. The true relationship is that curved one, but if I am restricting my range, I am not going to see that in my data. So always be considering, have I collected the full scope of my data in my sample, and what does my data look like? The final issue with interpreting correlations that we're going to talk about really has nothing to do with your data. It has to do with the measures themselves, how you collected that data. And you can't necessarily see this through looking at the scatter plot or your Pearson R, Because if the measure you're using itself is not reliable, that if you had done this study one time and found one study, but then one answer, but then you do it a second time and it's a completely different answer, that means it's not reliable, and so you can't really use that measure. This is why we care so much about understanding the reliability and the validity of measures, this inter-item, inter-rater, and test-retest style reliability. Because if you don't have that reliability, then your correlation is not reliable either. And so you can't really hang your hat on any kind of finding you get from your study. So now that we've talked about the issues in interpretation, we of course have to talk about correlation does not imply causation. So you just took a statistics class? Well, maybe the class helped, right? Just because you took it doesn't mean it was the thing. Just because two variables are related doesn't mean that one is causing the other. There is not a definite link between them. Correlation does not equal causation. You heard it in your statistics class. You're going to hear it from me. I said the thing. The requirements in order to justify causation are three. The first is that there needs to be covariance between the independent variable and the dependent variable, those IVs and DVs, the X variable and the Y variable. As one changes, the other changes. That's what the covariance means. The second requirement of causation is that there is a temporal precedent. That means that one variable must precede the other. One effect must happen before the other. Otherwise, the secondary effect isn't an outcome. It is simply related to the thing. So you need to have your X variable comes first. And the third is that you need to control for confounds. That means that there is nothing else that could be an explanation of the two variables. So what we have found through correlation is the covariance. That's really the only thing we know so far, that if there's a change in one, there's a change in the other. So what we're going to look at number 2 is the directionality issue, which could be a reverse causality, that even though X and Y are related to each other, it could be that X is causing Y, or it could be that Y is causing X, and the relationship is in the opposite direction. So we can't interpret causation there. The other issue is this third variable problem, when you fail to control for confounds. There is something else, but we don't know what it is because we haven't measured it. And so the main way that you're going to deal with the third variable problem is by trying to measure other things, by thinking through what those confounds, those other variables that could be affecting the relationship, measuring them and including them in your study. But for that, we need to have multivariate analyses because we have a third variable, not just two, we have multiple variables. But I don't want to get ahead of myself too much because we still need to talk about an idea of regression. So I have mentioned relationship many times, and I have just briefly talked about prediction, and I said we're going to be talking about regression and prediction together. Well, here's that moment. The relationship between two variables is just that one changes, the other changes. But if there is a strong relationship between two variables, then we're almost afforded the chance to say that if we know something about one person's variable, about one variable regarding an individual, we can kind of guess or predict what their scores on the other variable will be. And so for this process, we use a linear regression. This is a method of predicting an outcome Y variable based on the relationship with a predictor X variable. So what we're going to do is look at the relationship between these two variables, X and Y, and then based on that correlation, we're going to kind of guess about a new person's scores, about a new person's outcome. So what we do, we take all the data, and we're going to plot a line of best fit through it. So I've used this term, it's just that linear relationship. The scatter plot has lots of data, and you're going to create a line that gets as close as possible to as many as possible of those dots. This equation has this line has an equation. You might remember from your geometry class or your algebra class, the equation y equals mx plus b. Maybe you're getting sudden chills. Oh, I remember that from high school. Y equals mx plus b. That means that the y variable equals the slope times x plus b, which is some intercept. And the same is true for a regression. The predictor is x, and for every 1 unit of m that changes, you get a increase in y, and the b is just where it crosses the axis. All right, so I just explained y equals mx plus b, but I have to apologize for statisticians everywhere. They like to be special. And so instead of y equals mx plus b, in all of the research you're reading, you're going to see something different. And it looks like y equals bx plus a. I know, it's the same math, just different letters. I don't know why, but it is. So we're going to use y equals bx plus a. The exact same thing is true about what they represent, though. Y is the outcome value based on all the math you're doing. A is the intersection, so this is the point at which the regression line intersects the y-axis, the intercept. The b is the slope, the rise over run, and the x is the predictor value that you have for the individual. With this regression equation, you plug in x and you get the value y. You put x times the slope, you add that intersection of a, or the intercept of a, and then your fancy math gets you y. B is the slope, as I said, the rise of the run, which is the amount that y changes when x increases by 1 point. Every increase of a value of 1, from a 3 to a 4 or a 99 to 100, that's going to change the y in some relational way. And that's where your correlation comes in. A is the intercept, which just means that if x is 0, that's the value of y. So again, I got to there that b is the slope, which has a lot to do with the correlation. I said the correlation is part of a regression, is used in there. Well, the correlation is used to calculate that b slope, that relationship. But let's first visualize what this regression is. Now, where does this y equals bx plus a come from? Well, this is, again, the regression line, and it's also known as a line of best fit. It's the equation that passes closest to all data points. We're drawing a line through all the data. We're trying to touch them. Now, no prediction is perfect. No regression line is perfect. We're just trying to make the best line that we can using what's known as the least squares method. So anytime you're drawing a line between a bunch of data points, there's going to be some kind of error that's in that line. And this is the sum of the squared distances between the data and the line. And what we're going to do is run analyses to figure out whether the line is good enough to use. So here I have a regression line that is just y equals y. So it is just flat, okay? And all of those little blue lines represent the error. And I would take each error between the point and the red line. I'm going to sum them and then square them and then add them up. So square them and then add them. It's the sum of the squared distances between the data and the line. And as you can imagine, there's going to be a really big amount of error in this equation, this line that's been drawn. Right? Those ones closer to the ends, that's a huge amount of error. If I square it, that's going to make even more error. It's a lot of error. It makes not a really good line. That is not a good representation of our data. But if I have an equation like this, so the 0.685x plus 21.522, that's the line I have going through all my data. And you can see all of the distances from the data points are relatively small. Yes, there's that one larger blue error at the far right-hand side, but all of the others are so small that when you add them up, this is the least errorful, the best fit line. It is the one that has the least squared differences, and that's why it's called the least squares method. Now, you don't have to necessarily do all of this data, or this math. You can. You learned in statistics how to do the math for a best fit line in a regression equation, but at this point, you can kind of let SPSS do it. But that is what the regression line is giving you. So let's say I've done a study looking at the relationship between age and alcohol consumption, and I've already done all of that math to get the best fit line. I've created the regression equation, and I can see here that's a negative relationship, a negative slope between the two variables. I collected it just for 21 through 51 in my study, and I can see that the younger individuals are drinking a lot more than the older individuals. But that's just the correlation, and that's an interesting regression. But now I want to know how a new individual, can I predict their drinks based on their age? So maybe I have a participant who is 26 years old, and I would just track them up here, see where they hit that best fit line, and track them over. So I'm figuring out, based on my X value of age and knowing the slope and the intercept, can I predict, can I do the math to figure out their drinking? So let's talk about a regression again, this time with numbers instead of the just visual scatter plot. So let's say, as an example, I want to know if SAT verbal, the X variable, can be used to predict SAT math scores. So I have a regression equation that tells me to input X to get Y. And here you have the X equal, or the Y equals BX plus A, and what I've added in that's a little special is that hat above a Y. Hat just means predicted Y. So there's an actual Y score, so I might know somebody's SAT verbal, and they do have an SAT math score that is related to their verbal, maybe, but they have a score on both somewhere out there in the world, but I might not know their math score. And so I'm trying to guess at their math score, but I'm not going to be perfect because no regression is perfect. There's going to be some amount of error. So what that Y hat, little cap on top of it, tells us is that this is not actually their Y score. This is our guess, our prediction about their Y score. All right, but let's say in my previous study, I found there was a relationship between math and verbal score. And I could come up with math to get an equation for how well verbal predicts math as 300 plus 0.7x. What this shows me is that the intercept, when x equals 0, when there is no verbal score, somebody would score a 300 on math. But then for every 1 point of verbal score that we increase, there's going to be a 0.7 increase in our predicted SAT math, that 0.7 increase in Y. So if John, this new person who I didn't have as part of my previous study, had an SAT verbal of 600, what can I predict is the SAT math score? And this is a simple matter of plugging in the numbers. So I'd take that equation, and instead of X for verbal score, I would put in 600. I would multiply 0.7 by 600 and add 300, and I would get an Y hat, or a predicted Y score, a predicted SAT math score of 720. That's all it's doing. Okay, it's just saying how much am I increasing on X and where's the intercept, and now I have an idea of what Y is. Let's take a breath and do a quick review. So a bivariate correlation tells us the relationship between two variables. We talked a lot about ways to interpret and problems with interpreting based on your data or based on issues of causation. We then talked about regression, which is when you utilize the relationship between two variables in order to predict scores on one variable from the known scores on the other. So throughout all of these, we're just talking about relation and correlational ideas, and so we still have, there's no causation. And that's going to be true pretty much forever when we're talking about correlational research. But we do want to get better ideas, a better argument for why there might be some causal link between two variables. We can't know, but we do want to see if we can explore more. So we are always on the mindset of, what if there are alternative explanations for relationships between two variables? That's that number 3 issue for causation, that something else is the real relationship. Even though you found a correlation between two variables, or even though one variable can significantly predict another, what if it's because of error? What if something else is happening? And that's when we get into the final part of today's slides, which is multivariate design. So in multivariate design, we are looking at correlational studies that involve more than two variables. And the main approach we care about is called multiple regression analyses. So I've talked about regression, which has prediction. So really you should always associate regression and prediction with each other. But now we're using multiple variables to predict an outcome. So the definition is just that. We're predicting an outcome from more than one predictor variable. You have one outcome, but multiple predictors. And what this is doing is it's attempting to narrow down the relationship between the outcome and the predictor. So there might be a third variable or multiple variables that are really explaining the relationship. For instance, I might have a relationship between GPA and self-esteem scores like we've been talking about in the slides so far. And I might have a correlation there, and I might have some regression where I can predict self-esteem from GPA or maybe GPA from self-esteem, but it might be that there's something else going on that's causing that relationship. And it might be directional, it might be not directional, we don't know, but there might be other variables such as how important is the grade to the individual? If the individual doesn't care, does that affect their self-esteem? What if they're going through general heightened levels of stress? Will they have worse self-esteem with a worse GPA? Will they be less affected because they have other things happening in their lives? And what if they're just a generally positive person? Does that provide some kind of mental protection against GPA changes leading to self-esteem score changes? So if we are trying to establish a causal link between GPA and self-esteem scores, we need to first rule out that these other variables are having an effect, are actually the thing that is causing that relationship. If we have taken away every other third variable item, if we have ruled out every other possible causation, then we have a stronger case for the causal relationship between GPA and self-esteem scores. When talking about multiple regression analyses, you're often going to hear the term controlling for. This means that when you're doing an analysis, you are trying to hold that third variable constant while still investigating the associations between the other variables. So you still want to see the relationship between GPA and self-esteem, but you want to make sure you're accounting for positivity. You're maintaining a certain level of positivity in your scores to see if the relationship is still the same between your primary variables of GPA and self-esteem in this example. So the question in your head might be, if I'm just talking to people who are generally positive, is there a relationship between GPA and self-esteem still? Or what if I have people who are generally negative? Or what if I have people who are generally in the middle of the positivity negativity spectrum? The idea being that if you're holding it steady, and people who are positive or negative or self-esteem, it doesn't really matter where they are on that positivity negativity spectrum. If all of those people still have the same relationship between GPA and self-esteem, well then, positivity is not the explanation. You can rule out positivity as the third variable. So again, if yes, if it's still generally the same relationship, you rule out positivity. But if no, if you are seeing changes based on the positivity, well, this will undermine the hypothesis. If it only turns out that the GPA self-esteem relationship exists for negative people, well, then that negativity is a variable that might matter. So trying to look at and controlling for this third variable helps to back up and support your hypothesis. And like all good testing, you're not necessarily looking for confirmation, you're looking for falsifiability. You're looking for ways to undermine that hypothesis, to falsify, to prove wrong, and that's what this test is doing. Some more terminology that you need to know for multiple regressions are first the criterion word. Criterion is the new word for an outcome variable. It's also associated with the dependent variable. So it is the thing you are trying to predict. In our example, that's the self-esteem. We're trying to make an argument that I can use other variables to predict the criterion variable of self-esteem. The things that are doing the prediction are the predictor variables. This is the same thing in a regression. So these are the variables that might be causing the change in the criterion variable. It's the same as an independent variable or an IV. In our example that we're using, it is GPA and positivity. We have a hypothesis that those variables are somehow having a causal effect on self-esteem. Other terminology is the beta A beta is a statistical representation of that relationship between your predictors and your criterion. And each predictor to criterion variable has a separate beta. Just there's a relationship between GPA and self-esteem. Well, there's a beta describing that relationship. But there's also a beta between positivity and self-esteem, a relationship there. This is similar to an R in a bivariate correlation in that it represents the relationship and it ranges from that -1 to +1, and it has an associated p-value. Very similar, they're just calling it something different because it has a different method of calculating a beta. But interpretation of the beta is the same as interpretation of an R. The only difference is that this relationship, this beta relationship, this beta value, controls for the other variables. It's discounting them. So when we look at the beta between GPA and self-esteem, that is saying what is the relationship between my X variable of GPA and my Y variable of self-esteem when I am holding positivity constant, when I am controlling for positivity. I'm removing positivity as a third variable from this relationship. So if the beta is still significant, even when I am ruling out positivity as a third variable, well, that's going to add support for our relationship between GPA and self-esteem. So here's an example with numbers, kind of what I was just describing. If I was just to do the analysis between GPA and self-esteem score as a correlation with a Pearson R value, I might get a -0.3. See that there's a negative, moderate to weak relationship between GPA and self-esteem. But when I bring in positivity and I run the same analysis, this time controlling for positivity, my beta might turn out to be a -0.01. So here I'm seeing that, oh, after I've controlled for positivity, my relationship between these two variables disappears. It goes closer to 0. So that means that positivity might actually have a significant effect, might be a third variable explanation. So I can't generate causality between GPA and self-esteem, but I wouldn't have known that. I wouldn't have known that my original R score was incorrect unless I had controlled for positivity and run this multiple regression. The best part about multiple regression, and my favorite part, and why I actually use multiple regression all the time in my research. Correlational studies are fantastic. Regression is fun. Multiple regressions are an answer to everything because you can control for more than one variable at a time in order to rule out multiple third variables all in one big scoop. Remember that the beta statistic represents the effect when controlling for any other variable that you're included. So you could run the analysis between GPA and self-esteem and control for all three of those extra variables, and whatever the final variable, the final beta that you get between your two main predictor and your main criterion variable, that will mean something special, right? That will mean that all things held constant, all things held and controlled for, all things you've tried to explain and see if they're the real reason, and then if they still aren't, if you still have a relationship, that's awesome, right? That gives so much support for your causal link between two variables. Now, it doesn't answer that causal link, but it does provide more support. So as a note, I want to kind of reiterate what I just said at the end. You cannot establish causation ever with a multiple regression. And this is for two reasons. One, there might be still temporal precedence, that issue number 2 that's called into question, and there might not be all of the things controlled for. There might be a new third variable that you just didn't think of. So researchers are constantly trying to think through what could be other third variables that I could include in maybe a multiple regression analysis to help to find another study that supports or doesn't refute the idea that there's a causal link between these two variables, that if I can't defeat it, then I haven't falsified it yet. I keep trying to falsify, I keep trying to find a new explanation that really explains the relationship between two variables. And if, as researchers, we keep failing to falsify, well, that gives us a lot of support for our theory and for our hypothesis. While we are in the thick of correlational research and talking about multivariate analyses and multiple regression, now is the time when we should address the idea of mediation. A mediator is any variable that explains the relationship between two variables. So as before, we were controlling for and saying that, oh, it might affect the relationship. Here, a specific mediator is affecting the relationship, but it's specifically answering why is there a relationship. That the entire explanation, the entire path between one variable and another is explained because something happens in the middle. The mediation involves the correlations and multiple regression for us to test whether in fact a variable is a mediating variable. So as an example, I might have a question about whether kids are healthier depending on whether they go to recess or they stay inside writing. So I'm going to collect students who are ranging from having a lot of recess time to having very minimal recess time and just going inside and writing down and thinking through all their test exams. And I might find that there is a correlation between the amount of recess time with health. So whether they're spending more time outside or more time inside, there's a correlation with health. And I could publish that alone. There's a relationship. That's a correlation. Look, recess is good for health. But there might be a reason why having recess is good for health. And I might have a hypothesis that it's because of the physical activity that happens. You see how it's a why here. It could be that it's the fresh air is the reason it's good for health. There could be that the touching a hula hoop is the reason and the why for a connection between research and health, though I don't think that's as good of a theory. But my idea is that it might be physical activity. In order to test mediation, we need to follow 4 steps to find out whether we have a predictor variable that is in fact explaining the relationship and is the only reason that these two variables are related to each other. We take 4 steps. The first is that we have to establish a relationship between our initial variables. This is known as the C relationship. This is like the original study I talked about, where we're seeing whether having more time at recess is correlated with health. And that's really all this is. It's a correlation or a regression, but just with 2 variables. Is there a connection there? So this is your test relationship C. We then are going to include our other variable, which is physical activity. And we're going to test this relationship known as relationship A. And this is saying, does more recess also relate to physical activity? The hope in my researcher mind being that the ones who are outside are getting more physical activity. I think that'll be a pretty strong correlation there. Then I'm going to test my B relationship, where I see, does physical activity relate to health? If someone has more physical activity, are they healthier? It's important to note that so far, all 3 of these test relationships have been bivariate. They can be a correlation or a regression, but we are just trying to see, is there a relationship between these variables, individual sets. The 4th step, though, runs the multivariate analysis, or the multiple regression. Here we run all 3 variables at the same time, and we see a new test relationship called C prime. It has that little apostrophe after it. So it's saying modified C, basically. And does this new C prime hold up? Is it still there even after I'm controlling for the mediator? So I knew there was a relationship between recess and health, but I also know there's a relationship between recess and physical activity and a relationship between physical activity and health. So now when I am including physical activity and asking, is the whole relationship of C actually just physical activity? Is it a path from A to B to health? Does C prime still hold up? And if it does, great. Then there's still a connection between recess and health. But if the new C prime, that new multiple regression, is now non-significant, whereas my first test relationship C was significant, well, now I know that the actual relationship is explained by physical activity. And I know that physical activity is a mediator. So we use these mediation analyses, these special forms of multivariate and multiple regression, in order to help inform our understanding of the causal link between variables by including this y variable. But we can't fully infer causation, and there's some other issues with mediation that we need to keep in mind whenever running these analyses. The first is, what are the requirements for causation, which is that you always need to understand and assess the temporal component, that for causation to exist, one of the variables needed to have been affected or to have changed before the outcome variable. The predictor needs to have experienced variability that then resulted in variability in the outcome. And the only way to really do this and know for sure that one was happening before the other is through the manipulation of your predictor variables. And that can only happen if you're manipulating both, or it's best if you are manipulating both. This is something we're going to talk a lot about with experimental methods, which correlations can't do. There's no manipulation in correlational research, but experimental research gives you some flexibility of manipulation. We should also keep in mind the comparison of the C versus the C prime. How much of a change between C and C prime really constitutes a mediation? That if there's a drop of 0.01 points versus a drop of 10 points, what does that mean? Because all of these values are really interpreted in a context. So there are a lot of statisticians out there who are trying to find out with complex ways of comparing the C versus C prime. But at the end of the day, there is no tried and true way of saying, yes, this is a mediator, this is not. We simply look at it and try to interpret based on our experience and our knowledge of the variables about whether the change between C and C prime is enough for us to inform our hypothesis. There's also a difference between mediation and third variable. I have been using mediation to describe when there's a causal relationship between two things. It's explained by this third variable, that specifically a third variable about causation, whereas a third variable problem is just that two things seem related, but really they're not. There's something else out there in the world that's really the relationship, and you haven't measured it. A mediator needs to be measured and needs to be input in this equation. And then finally, there's also moderators. A mediator is the why question. Why is X related to Y? But the moderator is the when or for whom. So this is showing that the relationship between X and Y is different depending on the context. So it might be that only negative people see a relationship between GPA and self-esteem, or only positive people see that relationship. Remember that curvilinear graph I showed you between GPA and self-esteem? Well, maybe it's only people high self-esteem experience this negative relationship, whereas people with low self-esteem experience a positive relationship. There's the when and for whom is contextual. Why is the causal relationship, when and for whom is the contextual. All right, but those are the main issues to keep in mind with mediation. It's still a fantastic way of analyzing, and we're going to talk a lot more about the other moderation when we get into experimental methods, which give you a lot of that control over what groups you are looking at, so you can do these when or for whom. So that's all for today. You have learned a lot about correlational research. Again, next time we're going to start getting into experimental research, but for now you're looking at bivariate correlations, those two variables, two continuous variables related to each other. The regression, where you take it one step further to do some prediction based on your relationship between those two variables. And then finally, the multivariate analyses, where you're taking those correlated variables and trying to inform causal inferences about that relationship. All of these are excellent ways of understanding particularly continuous data, and we will move on to experiments where you get to more manipulate to help deal with those causal issues. Have a great week.